All right, let's talk a little bit about work. So this is section 6.6. And I am not going to get into a whole bunch of nitty-gritty details about this. Um, in my opinion, that should be reserved for a physics class or an engineering class. However, it is appropriate to at least kind of to talk a little bit about work because it's one of the many applications for integration, and you'll see why. So first of all, to just get our bearings a little bit, when you push a stalled car for a certain distance, you're performing work, and the effect of your work is to make the car move. The energy of motion caused by the work is called the kinetic energy of the car. So there's a relationship between work and energy, right? Okay, but going back to work, so the way that we define it in physics is as follows. If a constant force of magnitude F is applied in the direction of motion of an object, and if that object moves a distance d, then we define the work, W, performed by the force on the object to be W equals F times d. So work is force times distance. So common units for measuring force are newtons, which get a capital N, dynes, which I had never heard of actually before I prepared this section. So they say they're common, but I'd never heard of them before. Anyway, dynes and pounds. Pounds, of course, I had heard of. So newtons and pounds are really, I think, the most commonly used ones. Newtons are the ones used in the international system for weights and measures, right? So the SI units are newtons. Anyway, so that's just the force. Now, work is force times distance. So obviously, work is going to have units of force times distance. When you're dealing with newtons, the distance needs to be converted into meters. And Newton meters are called joules. Okay? Dyne centimeters are called ergs, apparently. And then pound feet. Now these ones get a really creative name. Pound feet are called foot pounds. Anyway, so those are the units when we're talking about work. Okay, so just to give you a simple example of this, right? Let's say an object moves 25 meters along a line while subjected to a constant force of 4 newtons in its direction of motion. Find the work done. Okay. So an object moves 25 meters. So the work done is the force times the distance. In this case, the force, we're told, it's subjected to a constant force of 4 newtons. And the distance, we're told, is that it moves 25 meters. So that would be 100 Newton meters, or in other words, joules, right? Right, 100 Newton meters. Okay, and that's it, right? That's all there is to it. Now, that obviously didn't require any calculus, so you may wonder, well, where does the calculus come in? Where does the integration come in? Well, the integration comes in because oftentimes we're not interested in a constant force. Oftentimes we're actually interested in a variable force. For example, and there are lots of examples of this, but for example, if you pull back on a spring, then the further you pull, the harder it is to continue pulling it, right? The further back you pull, the more force is required to continue pulling. So the question is, how would we calculate the work required to move a spring from its equilibrium position back to a certain, distance from equilibrium, right? So that's gonna require a variable force. So how do you calculate the work done in making that movement? Well, so here's how we do it, right? So suppose that an object moves in the positive direction along the x-axis over the interval AB while subjected to a variable force f of x. then the work done on the object is the integral from a to b of f of x dx. Now, a formal proof of that fact can be found on page 377 in the textbook, but intuitively, the reason for this is because at any given distance x, the force being applied is f of x. Okay? When we integrate over AB, we're basically multiplying each individual force at each individual distance x by the length, right? By the distance that the object travels, right? So we're basically multiplying by the distance that the object moved. So in a way, if you squint at it just right, this is force times distance, okay? It's just that the force is variable. Again, if you want a less hand-wavy explanation and a more formal proof, take a look at the textbook on page 377. But so let me give you an example of this. So example 2 says, find the work done by a force f of x equals x plus 1 on a particle that moves from x equals 0 to x equals 5. Okay? Okay, so the work done is going to be the integral from x equals 0 to x equals 5 of f of x equals x plus 1. So x plus 1 dx. All right, and that's all there is to that one. I mean, obviously we have to integrate, right? X squared over 2 plus x from 0 to 5. That's going to be 25 over 2 plus 5 minus 0 plus 0. So, you know, this would be 10 over 2, so 35 over 2, we could say. 35 over 2 what? Well, it didn't actually tell us, right? We weren't given a unit of measurement here or here. If we called this newtons and we called this meters, then it would be 35 over 2 joules, right? Or if we called this pounds and we called this feet, then this would be foot-pounds. Okay? But anyway, that's that. Okay? One more thing I want to cover here, and again, I'm just scratching the surface. So this is going to be kind of another short lecture. But the last thing that I want to talk about is Hooke's law. A spring that is stretched x units beyond equilibrium pulls back with the force of f of x equals kx, where k is a constant called the spring constant. K is going to be different for each spring. It depends on, you know, how thick the spring is, what material it's made out of, right? Things like that. But what's interesting and what Hooke showed is that the force required to pull a string at any given distance is going to be directly proportional to the distance that it's pulled, right? So it's not inversely or something like that. It's directly proportionate. So okay. So with that in mind, then let's do one last example. This one says a spring exerts a force of 5 newtons when stretched 1 meter beyond its natural length, or in other words, beyond its equilibrium. Let's find the spring constant K, and then let's answer the question, how much work is required to stretch the spring 1.8 meters beyond its natural length? So here we go. So the first thing we want to do is find the spring constant K. By Hooke's law, we know that the force required to that the force with which the spring is going to pull back is f of x equals kx. We also know that it's exerting a force of 5 newtons when it's stretched 1 meter beyond its natural length. So when x is 1 meter, the force is 5 newtons. So we know that 5 equals K times 1. Or in other words, K equals 5. Right? So the spring constant is K. The spring constant K is 5. Okay? All right, now part B asks, how much work is required to stretch the spring 1.8 meters beyond its natural length? So here you might have to imagine like a spring, and maybe the end of the spring is at 0. We'll just say that the end of the spring is at 0 when it's resting, right? When it's at equilibrium position. So we want to know, if we pull it back 1.8 meters, how much work is required to do that. Okay? So the variable force here, we know, is going to be 5x, right? Because Hooke's law tells us that f of x is kx, and we just said that k equals 5. So f of x is going to be 5x, and the work done is going to be the integral from 0 to 1.8, because we want to pull the spring from equilibrium out to 1.8 meters beyond equilibrium. Okay? And that's that setup, right? So it's not terrible. This is going to be 5x squared over 2 from 0 to 1.8. And since this is an application problem, and since you were given decimals in the original problem, I'm going to go ahead and give you decimals as your answer. So this is going to be 5 times 1.8 squared divided by 2, and that comes out to 19.6. The force was given in newtons, and the length was given in meters, so this would be joules, right? This would be Newton meters, or in other words, joules. Okay, that's all I'm going to say about this. The book goes into a lot more complicated examples, how much work is required to pump water out of the top of this crazy shape and all of that stuff. Again, if you're interested, you can kind of read through the textbook to see those kinds of problems. Otherwise, you'll see those kinds of things in physics or engineering, and I think that's the appropriate place to house them. So that's all I'm going to say about this topic.